Hello, I am Pranav. Today we will be discussing about Shor's algorithm and how this Shor's algorithm completely revolutionized today's industrial encryption standards and how it completely destroys and invalidates them. Okay, so before we see how this Shor's algorithm works, we need to understand how today's current encryption standards work. So today's encryption basically is changing some data into an unintelligible form such that any unauthorized intruder or person cannot understand what that message or encrypted data is trying to say. And this is based on a principal factor that we have to essentially make sure that encryption is very easy, but decrypting, reverse engineering or decrypting for that intruder is very difficult. So how this is achieved is based on some difficult to solve or hard mathematical problems. These difficult to solve mathematical problems are currently, as it says, very difficult to solve even using current computational techniques and powers. So for example, one popular encryption standard we have is RSA. This RSA works on the difficult mathematical problem, which is prime factors. So because of these prime factors, it is very difficult to reverse engineering RSA. So how this works is, in RSA there will be a very large number, say n. This n will be a prime factor, is a factor of two prime numbers, say a and b. And the thing is that the encryptor can easily find n by multiplying a and b, simple multiplication. But for the decryptor, finding this a and b using n is very difficult, even for today's computer. Because, for example, say take these numbers will be very big, like 200 plus digits or even more for n. So if we take one computer to find this a and b, it will take more than thousands and thousands of years to calculate this a and b for this very large prime number. For a large number, finding its constituent prime numbers, so it is very difficult. And how these people, this decryptors, how they'll essentially brute force. They will try one by one. Is this number is the prime factor one by one. So it's a brute force technique, and it will take lots of resources and time to decrypt it. So essentially, it is very difficult to solve this prime factor problem. So that is how today's encryption works. This RSA, Diffie-Hellman uses discrete log problems. So these encryption techniques all uses difficult to solve mathematical problems. So this today's encryption standard very secure. It is not worth the effort to build very large infrastructure to decrypt these problems. But now in this today's world, we are going into quantum computing. And quantum computing, essentially there's a misconception that it is a very powerful version of normal computer. It isn't that, but some things it can extremely efficiently do what normal computers can, and the Shor's algorithm is one example of that. So let us take this prime factor. The source algorithm is for the finding this prime factor only. So we will discuss how it works. So essentially, this source of algorithm makes it very easy and ridiculously fast using quantum mechanics to find these prime factors. So as I said previously, for a normal computer, which it takes thousands of years, for source algorithm and quantum computer, it will very quickly give our answer. So how we will find, we will see. So how we will start with our very large number n, and our goal, this decryptor's goal, is to find this two factors of n, which is normal, very difficult in normal computers. So uh, first we will start with the normal method. As I said, this RSA, they will use brute force method only. They will randomly guess. So like that, we will randomly take a guess g. This g is our random guess, such that using this we need to find the prime factors. But normally, since that n is very large, the chance that this random guess g is a factor of n is very 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 low, very minutely low. So this g is most definitely is a wrong guess, we know that. But the goal of this our goal is to change this g into a g1 such that this g1 will definitely be a factor of n. How we will do this? Okay, as I said, this we need to find the factor of n, but technically we don't need to find the factor of n, we only need to find a shared factor. Shared factor means, for example, if we have 10 and 6, the factors of 10 are 2 into 5 and the factors of 6 are 2 into 3. So even though this 6 is not a factor of 10, both of these has a common factor of 2. And we might be wondering how this shared factor helps us, because we already have a very amazing technique known as Euclidean's technique, Euclidean's theorem and such. With this Euclidean, we can very easily find shared common factors, and with share, if we can find the shared two numbers which have shared common factors, then using this Euclidean, we can find, for example, in this example itself, if we if our n large number n was 10 and we randomly guessed and found this g as 6 such that it has a shared factor with 10, so using Euclidean we can find that the shared factor will be 2. So we will simply divide this large number 10 by 2, so we will get 5. So essentially, just by finding a number which has a shared factor with n, we find both factor. We can find both factors of this n. So this for us, which this means that we just need to find shared factors, and this with the shared factors we can find the normal factors of that large number n and decrypt everything. But even this, as I said, the chance of randomly guessing a shared factor, even a shared factor of a large number one, is very small. But this is, as I said, we need to convert this wrong guess g, which will definitely not be a shared factor or a factor anything, into a correct guess g1, which most probably will be a shared factor of n. How? So how we will achieve this is based on a simple technique. There is a simple concept where such that if we take a and b, such that a and b does not have a shared factor, but this it says that if we take a and multiply a with itself with n number of times, eventually this will be equal to a multiple of b plus 1. So we will demonstrate this with an example. For example, we will take 3 and 10. We can simplify this as a power to some power p will essentially be equal to multiple of b plus 1. So this example, if you take 3 and 10, does not have any, is not factors, have not factors, and they don't have any shared factors. But if we take the power, for example, if 3 square, it is 9, which can be also be written as 1 into 10, 1 into 10 minus 1, which is not. So we will take next 3 cube, 27, which is 2 into 10 plus 7, which is also not what we want. But next we take 3 power 4, which is 81, and this is, we can write it as 8 times 10 plus 1. So essentially, here we take one a and we multiply it with itself n number of times. Essentially, for some power p, it will be a multiple of b plus 1, and this will be true for all numbers. So using this mathematical property, we can say that if for our random guess g, which as I said is a wrong guess, but if we multiply it with itself n number of times, say that power n, eventually it will be equal to a multiple of n, which is our large number. We have to find the prime factors of plus 1. So with that technique we can say that if we take our random guess and mm, power it with a power p, it will eventually it will be a multiple of n plus 1. And we can further simplify this equation. For us we can write this as g power p by 2 into g power p by 2 g power p by 2 plus p by 2, which is essentially g power p by 2 into g power p by 2. And we can even further simplify this by adding, and in maths when we don't know how to further simplify it, we will just add some value. So we will add and subtract g power p by 2 such that the equation will remain the same. So plus g power p by 2 minus g power p by 2. Then here we will we will rearrange this and take one common factor. Here we will get a g power p by 2 plus 1, and here what we will do, this minus plus 1 in this equation we will take this side, so there will be minus 1 here, and here we will get g power p by 2 minus 1. This is 1 into, so it will be 1 into g power p by 2 minus 1. This will also be minus 1, sorry. So g power p by 2 minus 1 plus 1 into g power p by 2. So these are also factors. So essentially finally we will get two factors such that g power p by 2 plus 1 into g power p by 2 minus 1 is a factor of, is a multiple of n. This is the final equation. We can simplify this equation, this equation into this type. So here see, here we get that some value into some value, we will get a multiple of n. So what is some value into some value? This is essentially factors. We can say that this can be a factor of n, which is what we need to find. So what we need to find, two numbers such that multiplying those two numbers will get n. So this is what we want. We want to find that something into something will get n. But this essentially need not be, this most probably will not be a factor of n, but it will be a multiple of factor of n. So a into factor, a into factor, p into factor, which is m into factor, because we are not, this into this is not n, something into something is a multiple of n. So this factor will also most probably will be a multiple of factors of n. Now this is not as a issue, because as we have already said, we only need to find numbers that have shared factors. So since this is a multiple, this will multiple of factors of n, they both will have a shared factor. And since we have established that with Euclidean theory, we only need to find numbers that have shared factor. So we only need to find this. But if we can find this, we already found factors of n, but up until now there is no quantum mechanics involved. So why quantum, why in quantum mechanics? Essentially there is three problems with these techniques. So first problem is that uh, this A into F and B into F, that is factors of n, we said that it can be a number which has a shared factor with n, but sometimes this number may itself be a factor of n, not a shared factor of n, but a factor of n, which would mean that B into F will be a factor of m, that is that multiple number. But if we get like this, then we won't be able to solve. There is no use for us. And the second issue is that power, this power need to be an even number, because if power is an odd, then p by 2 will be a fraction, and powers of fraction will be a whole number, not an integer. We need integers, not decimal numbers or fractional numbers. So these two problems means that if we get that factor of n or p as odd, then we won't be able to solve. But this is not an issue, because even if you get like this 3 out of 8 times, that is 3 out of 8 times, we will definitely we will be able to get the right numbers, right numbers. So essentially, which means that this is very good, because if we only need to do less than 10 times to get a correct answer, so which is very good. So we won't need that much computational power. So even though these problems exist, we can just retry it, and within 10 tries we will be able to solve it. But the issue comes in the third problem. The third problem is that what will be the p. So as we are specialists, we need to find p such that this g power p such that it will be a multiple of n plus 1. What will be this p? So uh, in one previous examples we have seen for 3 and 10, this since this was a small number, easily we will be able to find. Here p was 4, but as I said, this n is a very large number, so it may have 200,000 digits, whatever. So finding this p is extremely difficult in normal computing. Essentially we need to brute force it again, like is p1, is a p3, is p7, is p like that. We need to find, check each and every number, which will take such a long time that this whole algorithm is useless, because we can then use normal brute force instead to find the prime factors. Why we need to bother this? So that was the case until now, but this is where this quantum computing comes in, and this Shor's algorithm comes in. So how? We will see. So what is different from this quantum computing, how it is different from normal computing is that in normal computing, say you give an input and it goes into a normal computer, we will get one output. But in quantum computing, if we give an input and we will give it to a quantum computer, we will get a superposition of outputs, says O1, O2, O3. Will be large number of outputs. It will be, there is a superposition of outputs, and randomly the final output will be one O itself. But how it will randomly take from this based on probability. Based on probability, it will give a random number from among these superposition of outputs. But so this is not reliable. So how they make this quantum computer reliable is that they will use some techniques to eliminate these wrong answers, or wrong answers will eliminate themselves, and finally the final answer will most probably will be right by eliminating these wrong answers. So this same technique we can use in our to find p. So as I said, we need to find p such that it will be a multiple of n plus 1. So we will set up a quantum computer such that in this quantum computer we will input one random number. One number we will input in this quantum computer, and what will quantum computer will do? it will find that wrong guess to the power of this number, and we will get both. We will keep track this power and this powered number, and it will compare with m power n plus 1 and give output how much larger this g of x, how much larger than this multiple of n plus 1 it is, any multiple. So how much larger it is, say we will say that it is r or a remainder r. So it will calculate g power x and find how much larger from multiple of n plus 1 it is, and we will get 1 r. This is actually traditional computer. We will get do this in traditional computer. What quantum computer actually will do, instead of giving one remainder, what it will do, it will calculate for all possible numbers. So g power 1, g power 2, g power 3. So superposition of all possible numbers it will calculate, and it will give s1 g1x g power 1, and for that one r1, then g power 2 r2. Like that, it will find for every number, it will find the remainder, which is how much larger it is from the multiple of n plus 1. So in normal computing, this is not possible, but in this quantum computing, it will calculate a large number, superposition of large number of outputs, and it will give out for every number, it will give that remainder. So with just this remainder, we can't do anything. So what we can do? We need another technique to make use of this remainder. So this technique comes from a simple concept that, as we said, we need to find g power p such that it is a multiple of n plus 1. But there is one we now we inputted g power x such that it will be n power n, instead of 1 it will be m power multiple of n plus r, because that was what we calculated. But there is a property that says that if we g power x, if we add p to the power, it will actually be a multiple of n, but this r will not change. So this will be true for everything. So g power x plus 2p also will be another multiple of n, but this r will remain the same. For any number you take, if you add p or n, add or subtract any multiple of p to x, that multiple of n will change, but the r will remain the same. So from this we can glean that p has a repeating property. P has a repeating property such that if we add it to the power of any number, the remainder will be same across all numbers, such that the remainder is greater than the multiple of n, and it will be same across all numbers. So what we can do with this repetition is, as I said, from that quantum computing, we get a superposition of numbers, and we will get lots of r's, r1 r2 r3, like that we will get lots of. Then this quantum computer will give 1 r as an output. With this 1 r, it will not give 1 r, it will give all such numbers such that all such numbers which have the same r. So x1 r, x2 r, x3 r. So like that, it will give every number which has r as a remainder, same r as a remainder. So as we know from the repeating property, x1, x2, x3, all these power numbers have a difference of p between them because of this repeating property. So we can say that all these x1, x2, x3, every such power number will have a difference of periodic difference of p between them because of our earlier property. So if we have difference of p between them, we can also say that it will be have a frequency of 1 by p between them. So essentially, if we can find this frequency, what this frequency between the superposition of numbers is, we can find P. And as I said, if we can find P, we can find the common factors of shared numbers which has shared factor with that large number and find the factors of n. So how we find this f frequency? We can find using mathematical concept Fourier transform, and there's a quantum version of this too. And using this quantum Fourier transform, if we input this f into this quantum Fourier transform, we will definitely get 1 by p. There's a lot of mechanisms inside this quantum Fourier transform, but essentially, if we input this frequency inside this, we will get 1 by p. And with this 1 by p, we can derive p, and finally, with this p, we can find g power p, and with this g power p, we can find g power p by 2 plus 1 and g power p by 2 minus 1. So these two will definitely be a shared factor, will be numbers which are shared factor with n. We can demonstrate this with one example. Say that previous example is 3 and 10. So we said that the p there, it was 3 power 4, so which was 81. So 3 power 4 minus 1 is 80, and 3 power 4 plus 1 was 82. Now this 80 and 82 are not factors of 10, but 80 and 82 has a common factor with 10. That is, from 80 and 10, we can derive the common factor. What? 80 and 10 has a common factor of 5. 82 and 10 have a common factor of 2. So essentially, just by finding these numbers which has a common factor with this large number, we can find the factors of this large number, which are 2 and 5, which are factors of this 10. So finally, we have using Shor's algorithm, we have turned this random guess that we took at first, which was definitely wrong, but we transformed it into g power p by 2 plus or minus 1, such that it will be, those two will be numbers which has a shared factor with n. Now, with this shared factor, essentially we got, with this we are able to find for this large number n, we are very easily able to find a and b, that is its constituent prime factors. And if we know encryption techniques, we know that with these prime factors, we can very easily crack any sort of encryption technique in this world. So, but why it is not happening is because currently our quantum computers are very small. We don't have very big and powerful quantum technique. But if someone is able to build a powerful quantum computer such that it is able to calculate using the Shor algorithm prime factors of a large number, any sort of data over the internet can be easily cracked. So this is why Shor's algorithm can easily destroy any sort of current encryption techniques. So this is Shor's algorithm. So what we can do to prevent this Shor's algorithm? So in coming years, these recent years, we are looking into something called post post quantum cryptography. Post quantum cryptography. What this post quantum cryptography is different from quantum cryptography. Quantum cryptography is basically cryptography we do on a quantum computer, but post quantum cryptography is cryptography that is done to prevent attacks from a quantum computer, that such as the Shor's algorithm. So we need to find and update our current standards such that in the future, when eventually and definitely when these quantum computers are developed, our standards are able to fight and defend against these quantum attacks. And so, the, how we can this post quantum cryptography? As I said, there is a misconception that quantum computers are a very powerful version of normal computers, but it is essentially not that case. Quantum computers have some very specific tasks that they can do very very well that normal computers cannot do. So we this normal encryption technique, as I said, is based on some hard to solve difficult problems. That is why they are difficult to crack. So we need to find some hard problems which are not able to be solved by both normal computer or quantum computers. So in recent studies and research, we have some hard problems they are looking into it, such as lattice method, hash method, etc. But these are recent studies, recent development. We are still looking to update our standards such that in the future we can find these difficult to solve problems and develop some post quantum cryptography such that we can in the future we can defend against these Shor's algorithm and these quantum attacks. So this is all I will have to discuss. Thank you.